Hi class. In this section, we're going to talk about Taylor polynomials and approximations. So let me give some background to this and kind of set this up. Suppose we wanted to find a fourth degree polynomial of this form. So a sub 0, that's just a constant term plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4th x to the fourth. Now this polynomial that approximates the behavior of this function, f of x is equal to ln of x plus 1 at so around x is equal to 0. Not the entire graph, just really close to x is equal to 0. All right, so if we make p sub 0 equal f sub 0, all right, and the first, second, and third, and fourth derivatives the same, then we would have a pretty good approximation. All right, so let's consider this right here. I've got the polynomial that I want to approximate this function around x is equal to 0. So here's what I'm going to do. I need to figure out what a sub 0, a sub 1, a sub 2, a sub 3, and a sub 4 are. That's my goal. All right, so I'm going to start with my function. I know that at 0, because remember, if I go back, I want it to have a pretty good approximation at x is equal to 0. So at f of x is equal to this. F of 0, when I plug 0 into this, I get ln of 1, which is 0. So my polynomial here, I notice that p of 0 is equal to a sub 0. And what I'm getting at here is I want a sub 0 to be equal to 0 over here, right? So my constant term here is just equal to 0. All right, now let's take the first derivative. So if I take the first derivative of this function, I get the following. Now if I plug 0 into the first derivative, I get 1. So now let me take the first derivative of this polynomial. Well, the constant term goes away. I've got a1, a2, or 2x because the 2 comes down, then the 3 comes down, then the 4 comes down, and so on. This is just the derivative of my polynomial function. But when I plug 0 into this, I just get a sub 1. So what I see here is a sub 1 is equal to 1 over here. That's what I'm saying. I get the second derivative. Again, I plug in 0, I get negative 1. Now I'm going to take the second derivative of all of this right here. When I do, I get the following. Now when I set this, the second derivative equal to 0, I get 2a squared. So solving, all right, a squared, 2a squared, I want it to be equal to negative 1. So divide the 2 over, and a squared is equal to negative 1/2. Now I'm going to keep following the process. All I've done so far is find a sub 0, a sub 1, a sub 2. Now I need to find a sub 3 and a sub 4. A sub 3, you do the same thing. All right, you take the third derivative. The third derivative, when you plug in 0, is 2. So take the third derivative of this now. I get the following right here. Now when I set this equal to 0, all right, when I plug 0 in for x, I get 6a cubed. So you can see by simplifying that the a cubed, 6a to the third, is equal to 2. We'll divide the 6 over, and a third is equal to 2/6. And I'm going to leave it unreduced for now. Finally, for the fourth derivative, I'll let you follow through on your own here. You can see that when I take the fourth derivative, set it equal to 0, I get 24a to the fourth, and so on. So a is equal to negative 6 divided by 24. So this is what I've got. I've got my polynomial p sub x. This was a sub 0, a sub 1, a sub 2, a sub 3, a sub 4. And notice that I still have the x squared, the x cubed, and the x fourth. Those are staying. All right, so it just simplifies and looks like this. All right, now I look at my original function. F of x is equal to ln x plus 1. If we plot both functions, we see that near 0, the functions match very, very well. So watch what happens here. So in blue here, I have my original function f of x. And p of x here, I have my polynomial right here that I've just discovered. Well, you'll notice that overall the shapes aren't the same, but if we zoom in right around 0 here, you can see that, gosh, this polynomial does a really, really good job estimating the graph of ln of x plus 1 around 0. And that's our whole goal. We want to get a polynomial equation to approximate these graphs. All right, so our polynomial here has this form, as you can see, f of 0 plus f prime of 0x plus f double prime of 0 divided by 2x squared, and you can see the pattern here. The cool thing is, or if you write it like this with the factorial symbols, so 0 factorial, 1 factorial, 2, 3, 4 factorial, this pattern occurs literally no matter what the original function is. So you can just use this very, very simple mathematical equation right here to find the whatever degree polynomial approximation. So this just happens to be the 4th degree polynomial, but you could do a 5th degree, a 6th degree, a 3rd degree, whatever you want. All right, this is what we call a Maclaurin series, and this is generated of f at x is equal to 0. But suppose instead you didn't want to look around x is equal to 0. So if we want the center of the series and its graph at some point other than 0, we get what's called a Taylor series. And this is centering it at x is equal to a. And this is the pattern here. And you can see it's slightly different, slightly different. It's f of a, f prime, and instead of just 0 times x, you get a times x minus a. Instead of 0, you get a. Instead of x squared, you get x minus a squared, and so on. And that's all a Taylor series is. So like p sub 1 would be the 1st degree polynomial, p sub 2 would be the 2nd degree polynomial, and so on. All right, let's do another example. Y is equal to cosine of x. All right, so let's go back and let's do this. Let's do a Maclaurin here. So f of x is equal to cosine of x, f of 0 is equal to 1, f prime of x is equal to negative sine of x, f prime of 0 is equal to 0. You can see the pattern that I'm doing here. I got second derivative at 0, third derivative at 0, fourth derivative at 0. So I've got f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and f to the 4th of 0. So just literally plugging it into that equation, all right, literally just following the equation, I get the following. And you can see I expanded the pattern out to the 5th and the 6th here because you can see how this goes. And this, when I simplify, is literally just what the pattern becomes, all right? Because this is the 1, and so on. And here's the x squared. The 0 cancels the x away. Remember, I'm multiplying this now by an x, so it keeps going and going and going and so on. So if I look at the graphs here, this is my original y is equal to cosine of x. Here's p of x is equal to 1. And then watch what happens as I continue to add terms. The graph keeps getting better and better and better to look like cosine of x. So the more terms we add, the better our approximations become here. Let's do another one. So rather than start from scratch, we can use the function that we already know here, like this. So instead of x, we just plug in now 2x. A little bit of a cheat here. And let's do this one. Let's do another one. Y is equal to cosine of x. And let's look at x is equal to pi over 2. So going through the same thing, the derivatives, and then evaluating them at that pi over 2. Plugging it very, very simply in here like so. Now the next thing we have to do is just multiply it and apply it right to the formula here. So the 0 goes away. I get negative x minus pi plus x minus pi over 2 cubed divided times 3. And the reason here I have this plus, right, is because right here, and so on. And that's just your Taylor approximation at a different point than x is equal to 0.